Hello everyone, welcome to lecture number 26. So in last class we have been discussing the solution of the energy levels of a diatomic rigid rotor. Okay, so we have already solved the phi part. So now today we are going to solve the angular theta part. So in last class we have framed the Schrodinger equation for a rigid rotor and we knew what H cap stands for, the Hamiltonian, and then we have broken the psi theta phi into two independent functions, function of theta and function of phi. So we have already solved the phi part, which is 1 over root over 2 pi e to the power I m phi, and what was left to solve was the g theta part. So the g theta part came from such equations. So those are two equations, solving one of which we obtained this part, and the other part was this, okay, that we have I have written here. So today we are going to find the solution. Not exactly we are solving it, but we will find the solution, just like the case of a simple harmonic oscillator, where we use Hermite polynomial to find some solution, but we did not exactly solve it. So the similar thing here. Now you see this differential equation cannot be solved by any direct method. Alright. So when it is solved, you see the beta value takes up something like this, L multiplied by L plus 1. Alright. And thus E is equal to H cross square divided by 2i multiplied by L times L plus 1. So now you see you are getting two quantum numbers. One is M and another is L. So you are already familiar of such quantum numbers for atoms, right? For example, M is the magnetic quantum number for atoms and L is the azimuthal or orbital quantum number. And when we finish the hydrogen atom later, you will see that these L and these M's will be identical. So this part we don't have to solve extra. Alright. So that's why it is very important that we understand that how the solutions for the diatomic rigid rotor came, because the interpretation of orbital quantum number and magnetic quantum number would exactly come from by solving the theta and phi part for a diatomic rigid rotor. Now the question is how to solve it. Okay, so we will just try to understand where it comes from without going into details. Alright, so to solve equation 1, what is done is usually we take a substitution. The substitution is we assume cos theta is equal to x. Alright, and so that the function of theta becomes the function of x dx. So why do we take cos theta? Because since theta varies from 0 to pi, the range of x also becomes 1 to minus 1. Alright, so when we put cos theta is equal to x in this equation, it takes up such form, right? So first we have the sine theta part, right? So the sine theta part actually becomes 1 over 1 minus x squared. That means 1 minus cos squared theta is actually sine theta. Then we have here g theta is equal to px, right? And so by substituting means we will multiply px on both sides, alright, and then finally we will get this. So we have this expression where we have already used the value of v beta, alright, and so we get a new equation. So what is this new equation called? So this new equation is called Legendre's equation. So during the early stages of the development of quantum mechanics, such kind of Legendre's equation used to find its place in various application field of classical physics. Okay, so people were already familiar in solving of such kind of equation, and then it helped Schrodinger to find a pathway to solve such complicated equation. So now, if we solve such Legendre's equation, the solutions, okay, so we write here, the solutions are called Legendre's polynomial. Alright, so the solution comes from a power series method. So the Legendre's equation can be solved using a power series method, and the solutions are called Legendre's polynomial. So these Legendre's polynomial actually are of two types. Okay. So one type corresponds to when m is equal to 0, and another type when m value is not equal to 0. When m value is 0, the Legendre's polynomial is actually the Legendre's polynomial. Alright? And when m value is not equal to 0, the polynomials are called associated Legendre's polynomial. Alright, so now we have two types of polynomial. One is the Legendre's and another is associated Legendre's. So now we are going to see what are the nature or types of these two types of polynomials. So therefore I'm going to clean the board and I'm going to write a few sets of information, basically some equations, to make you familiar that these are the Legendre's and associated Legendre's polynomial. Okay, so let's do that. So here I have written down first few expressions for the Legendre's polynomial. So it is defined as m is equal to 0. Whatever the PLX values we get, those are called Legendre's polynomial. And you see, when L value is 0, PLX is 1, unity. And when L is 1, P1x is x, and then followed by this, and then followed by this. So it's interesting to see that for L is equal to odd, the Legendre's polynomial becomes an odd function, and when L is equal to even, the Legendre's polynomial becomes an even function. And also there are some important properties that PLX are orthonormal, and we can prove the orthonormality later. That means P1x could be orthonormal to P0, could be with P2, with P1 with P3, anything. It's just like the Hermite polynomials, so they are individually orthonormal to each other. And also PLX can be normalized individually. So therefore, if we take the function PLX and the limits are -1 to +1, and if we try to integrate that, the integration value would give you this 2 over 12 plus 1. So what would be the normalization constant? Easily, so if we take the normalization constant as n, and the n value should be such that the entire expression becomes 1, and therefore the normalization constant should be 2l plus 1 divided by 2. Just means the reverse of it, because if we take the normalization constant and then the constant square, and then we do that, we will find this value. Alright, so these are all about the Legendre's polynomial for n is equal to 0. Now let's quickly take a look for the associated Legendre's polynomial where m is not equal to 0. So let's clean the board and let's take a look at the expressions. Okay, so before we move on, I must admit that once again I made a mistake. So the normalization constant should be root over of 2l plus 1 divided by 2. So I missed the root over part. It is very simple because it says that n square minus 1 plus 1 plx square dx, this value should be 1, alright? And the expression for this value is 2 divided by 2l plus 1. So therefore, n square should be 2l plus 1 divided by 2, and n should be 2l plus 1 divided by 2 whole root over. Alright, so this is how we can calculate the normalization constant. Alright, so sorry about that mistake. So anyway, let's move on to the associated Legendre's polynomial. Okay, so for n not equal to 0, the associated Legendre's polynomial is expressed like this: p subscript l superscript modulus m function of x. So here the modulus m means only the magnitude of m is important, not the sign. So that means whenever we talk m is equal to plus or minus 1, we only take the value 1. For m is equal to plus or minus 2, we only take the value 2. So this is the relationship between associated Legendre's polynomial with Legendre's polynomial. So this part plx is the Legendre's polynomial, and this part mx is the associated Legendre's polynomial. Okay, and this is linked with plx by this expression. And you see if there is the mth order derivative, and then if we solve that, we will get the first few associated Legendre's polynomial. So for p00 the value is 1, for p10 the value is x, hence cos theta, for p11 it is sin theta, for p21 it is 3 cos theta sin theta. Now later when you will see the exact solution for hydrogen atoms, okay, say for p orbital, pz, px and py, etc., you will find that such kind of expression would appear, and it all comes from the solution of the angular part, that is the g theta part. Alright, so now we are familiar about the Legendre's polynomial and associated Legendre's polynomial, in other words PL and X. So the thing is, what do we expect from that? I do not expect you to remember or memorize these long expressions, alright? But given the formula, you should be able to find out these values. Alright, so therefore your job is to first recognize the expressions, and number 2, understand how it worked. Okay, so those are the 2 things I want you to appreciate. Alright, so let's move on to the normalization part and the orthogonality part as a whole for associated Legendre's polynomial. So let's check it out. Alright, so here we go for the orthonormality conditions for Legendre's and associated Legendre's. So on the left hand side, I have the condition for the Legendre's polynomial. See, it is the limit minus 1 to plus 1 in terms of x, plx and pnx, where l and n are 2 different, it corresponds to the 2 different wave functions, dx, and then this corresponds to 0 to pi in terms of theta. And remember, the volume element is sin theta d theta, because in polar coordinates the volume element d tau, so in Cartesian coordinate the volume element d tau was dx, dy, dz, but in polar coordinate it becomes r square sin theta dr d theta d phi. And remember, this expression can be proved in the similar fashion from the derivation from Cartesian to polar coordinates. So this value should be equal to 2 over 2l plus 1 delta ln. This is the Kronecker delta. And now we go to the associated Legendre's polynomial, the orthogonality testing. This goes in the same manner, -1 to +1, and where we have, sorry, it should be, instead of L, it should be N, because here L and N represents two different wave functions. So in terms of theta, once again, it should be, sorry, 0 to pi. Okay, so it becomes 0 to pi. This PL cos theta sin theta d theta, and it would be equal to this expression. Okay, so we are already familiar of this part, and now this is L plus modulus m whole factorial divided by L minus modulus of m whole factorial multiplied by the Kronecker delta Ln. And at the end, this is the expression for the generalized normalization constant NLM. So here L stands for one quantum number and M stands for the other quantum number. So L is associated with theta and M is associated with the angle phi. So the quantum number corresponding to the theta phi part, Lm, so NLM is equal to this whole expression, and this expression is under the root over. Okay, so this is the generalized normalization constant. So now you see, whatever I told you today is basically I delivered a whole bunch of information in the form of a table to you. Alright, so we did not derive anything, because this particular solution, that means solution of the Legendre's polynomial, is the same like Hermite polynomial. It is beyond our scope and context. So we are just now interested on the outcome, that means the nature of the solution. So by now we have been successfully able to figure it out, both the angular parts, that means both the theta and phi part of the wave function corresponding to a diatomic rigid rotor. So now it's our job to summarize this. Okay, so summarize means we have to find out the final expression psi theta phi, alright, in terms of normalized manner. So this is equal to, as we already done, that is g theta and f phi. So we have already done f phi in the earlier class, and today we have solved the g theta part. Okay, so now we have to find the entire expression for g theta f phi under generalized normalization constant. So how to do that? Okay, so now I leave that matter to you for practice and for tryout. So you try out to find the general expression for psi Lm theta phi. Okay, what should be the expression psi Lm theta phi? So you please try to summarize based on this lecture number 26 and lecture number 25. So we will again come back to lecture number 27. So we will spend some moments to summarize and appreciate this entire finding. Remember, this is the most important solutions as long as hydrogen atom is concerned, because these theta and phi parts define the azimuthal and the magnetic quantum number of hydrogen atoms. So we would not need to discuss, or we don't want to learn it again when we come to the context of hydrogen atom. All right, so you please continue studying the textbook, and for any help, any query, I am always here, and don't hesitate to ask me. So for this week we have been covering a lot of materials, so please refer to all the materials and study it carefully. So I will see you again in lecture number 27. So till then, goodbye.